Hello everyone, my name is Susanne Scholz. I'm an application engineer at Vexel Imaging. Have now more than 20 years of experience in this field of data science and photogrammetry. And yeah, I'm the session chair for the computer vision talks. We have here 3 interesting talks about quite different application fields. One is the semiconductor, medical imaging, and urban planning. Yeah, I think let's start with the first talk of Isabell Dicillia-Kovatsch and Corinna Kofler. They both work in the field of semiconductors. So Isabella works at Infineon Technologies in the defect density group. And she has a DI degree from the University of Klagenfurt, as well as Corinna. She is a computer vision expert at KAI, Kompetenzzentrum Automobil- und Industrieelektronik. Yeah, and both have a lot of experience in this field, and I would like to hand over. The stage is yours.
Thank you very much. Well, thank you, Susanne, for that kind introduction. So we are very excited to be here today. And now let's dive into our presentation without any further ado. So actually, what is computer vision? Computer vision is an interdisciplinary field which aims to automate human visual tasks. And this is done by extracting meaningful information out of images or videos with computers, with the help of computers. And so how does this work? Well, actually here on the left image, you see what we as humans can see. It's just a picture. And computers, on the other hand, just see a huge matrix of numbers. And each of these numbers represents like 1 pixel in an image. And with these numbers, we can teach computers to do some really cool stuff. I show you now some of the techniques in the field we're working in. And the first one is that we can learn computers to recognize what they can see on an image. And this is called like image classification. And in this case, it's a cat. And furthermore, we could even learn the computers to localize the cat in the image. And this is then called like classification plus localization. And we could also learn the computers to detect multiple different objects in the images, as in this example here, cats, dogs, and ducks. And this is then called object detection. And finally, we could even learn them to know what kind of pixels belong to different objects in the image. And this is then called instance segmentation. So, and all these computer vision techniques are used in various different applications. And some examples here are, for example, self-driving cars, where computer vision is used to detect other vehicles, to detect pedestrians or road markings or traffic signs, and they kind of help you to drive safely. Computer vision is also, of course, used in healthcare. For example, in medical image analysis, they're used to assist doctors in detecting anomalies in X-rays, MRIs, or CT scans. And later on, you will get a bit more insight into this topic by Sapide's talk. Moreover, computer vision is used in surveillance systems. So those cameras are used for object detecting and anomaly detection, and just and computer vision systems or surveillance cameras equipped with computer vision can even alert authorities if they observe some suspicious behavior, for example. And then what we all use is like optical character recognition. In these systems, computer vision just convert PDFs or scans from papers or images into editable and searchable data. And last but not least, we have the field of manufacturing. There, computer vision plays an essential role in quality control. So it can be computer vision there is used to, for example, inspect products on assembly lines for defects. And today we are going to talk about an image classification, a project we are working in manufacturing. And more specifically, we are working on, so we are not working on images of cats, we are working in the semiconductor industry, and that's why we are classifying defects we see on semiconductor wafers during their production. And all the images we are working with, they are actually collected from wafers which are produced here in Villach, at Infineon in Villach, just 5 kilometers away from us. And yeah.
So in the semiconductor industry, it takes quite some steps in order to get from the bare wafer, which you can see here, to then a functional device later on, which is then built into smartphone, laptops, and many other devices. A typical processing sequence could, for example, be the deposition, a lithography process, the etching, and later on the cleaning of the wafer. There you always have the risk to get defects onto the wafer, which can then later on lead to fails of the device. In order to detect these defects already at an early stage, the defect density inspection is performed, and there you get defect images like the ones shown here. These are then classified manually at the moment. However, this is very prone to failure and also quite time-consuming. This would therefore be a great opportunity to introduce a machine learning model to also get a yield improvement and a more consistent classification. To get now from the idea to a working model, many key players need to be involved, such as the main experts, the data scientists, and machine learning engineers. These key players need to be already involved at the design phase, where the basic requirements are defined, where the data comes from, as well as a business case. Later on in the development, mainly the data scientists takes over the leading role when it's all about data preparation, model training, and evaluation. And lastly, we have the deployment into the production system, but doesn't end there. We also need to make sure that we have a model monitoring in order to detect failure already at an early stage. Now, starting with the design phase, here the domain experts takes over the leading role, and for example, basic requirements that need to be checked are where the data is coming from which type of inspection tools, what type of model we need. So do we need a very big model which can be used for multiple products, or do we need a very small one only for a very specific application? For the data availability check, we need to check the data access, as well as we have the right quality and quantity of the data. We need to group the data and label them later on. Lastly, we also have the business case calculation, where we need to make sure why this model helps to improve our current situation in the factory and how it leads towards an improved yield and quality.
So, and once the project is defined, we can start with the cool stuff. Which is like, first of all, so maybe not too cool, but, also belongs to data projects. We have to start with the data collection and preparation. Then the really cool stuff is the model development. Then we need to, of course, also check, is the developmental model okay for the production? And after this is done, we then also deploy our models in the production, but this will be explained a little bit later. So for now, let's focus a bit on the model development phase. And for the model development phase, we have basically two strategies. You can either use like a model-centric approach for training models or a data-centric approach. So a model-centric approach would be, for example, trying or training different network architectures or applying hyperparameter tuning to models. Whereas this data-centric approach focuses really on the quality of the data set. And the literature suggests to go, especially for real-world data sets, go with the data-centric approach, work on the quality of your data set to really get a model which works for your data and achieve a certain amount of accuracy you require. And then eventually, squeeze out the last few % by applying like hyperparameter tuning or maybe trying different network architectures. And this is actually what we do. So we started off like with collecting a bunch of data, and then we trained and evaluated model. Eventually, we figured out, okay, there are some classes which are low performing due to too few samples. We went back to this data collection, grabbed more, tried to gather more samples of this class, edit them, and trained the model again. Once we were happy with the first version of the model, we did a model check, which is basically applying the model to a completely new download of data from a different production period. This is very essential for us because with this check, we then realized, for example, okay, we didn't, in the previous production period, there was just some products maybe not produced, and we just didn't have those samples in the data set so far. So we, again, go back, collect the data, label them, train the model again. And this is quite an iterative process, which takes quite some loops. And for this model training, we can have, there are also two strategies, like either we train a model from scratch on our data or transfer learning. So, and the literature suggests also to utilize like transfer learning, especially if you have complex images, as we have, with a limited sample size. Then you can already utilize the pre-trained weights those networks have, and they have already learned to detect and recognize a variety of features, of high-level features and patterns, and you just need to retrain them on your specific images or on your specific domain, so to say. And this is what we most of the times apply for our models. And last but not least, I want to highlight or emphasize once more on the importance of this model check, which we always do, to just check if the model development data set is really representative for the production. And with that said, let's have a look at such a real-world data set distribution. And on the x-axis, you can see our defect classes, and on the y-axis, the number of samples in each class. And you can observe this data set is highly imbalanced. And this is the situation we always have when we work with data. And if we would train a model on such a data set, it would be biased towards the classes where we have enough samples. But this is not what we want. We want to have a model which works for all the classes, potentially, right? So, and to tackle this problem, we apply data preparation steps. And the first one of this is just being a resampling. So what do we do during this resampling? We just randomly sample images from the classes where we have enough samples and ignore the others. And from the classes where we have too few samples, we just randomly copy samples of them to increase the number of images in those classes. And we kind of experimentally found out that the resampling size of 1,000 works quite okay for our data set. And of course, just resampling is not enough. We want to increase the variety of the images in the data set, especially in the ones where we just copied the images. And this is basically done by data augmentation. This is essential because you want to have a generalized model. And this geometric transformation is basically just applying a little bit of shift or rotation, everything within a specified range, of course, so that it is still realistic for your data or for the data set. and you apply this to each and every single image which is fed into the model during the training phase. Yeah, and now let's have a bit deeper look to the models. So what we use to train our models are convolutional neural networks, also called CNNs, and those are a type of artificial neural networks which are used or commonly used for image processing or image tasks. And what it does is basically you feed an image through the network, and in the first series of convolutional layers, filters are applied to the images to extract features. And these features are then combined and processed in the fully connected layer, which then in the end classifies each image into one of the given categories. So we are here in a world of image classification. It's a supervised task. So for training those networks, we need a set of images along with their true labels, with their classes. And this is what we do, and these CNNs are actually state-of-the-art. They achieve good performance in these image classification tasks and are widely used in real-world applications today. And we use them here in Villach on a data set generated from scanning electron microscopes. So those are the tools who provide us these images. And they are produced during inspections in the semiconductor fab from all layers and wafers we produce here in Villach. And currently we have around 50 classes, 50 defect classes in our data set. And as already mentioned, we train CNNs. More specifically, we train, for example, efficient nets, pre-trained on the ImageNet data set. And as already mentioned, we go for the data-centric approach. And here is a summary of this iterative data-centric approach, what we did. At the beginning, we started off with a first version of our data set. Back then, we had like 23 classes in the data set, and trained a baseline model on this imbalanced data set just as it was. And then we also trained models, and prior we applied different data balancing methods to this data set. And with these experiments, we found out that if we apply this resampling, which I showed you, plus the data augmentation, that this works best for our data set. But yet we knew back then this is not, we're not yet representative for the production. And so therefore we worked with this iterative data-centric approach by just then adding more and more data to our data set, and finally at some point added up with a version 3 of the data set consisting back then of 37 classes, and we reached a validation accuracy of 92.7% already. But although back then we were not done yet, so still not representative for the production, we still had to add more images, because at that time also a new tool vendor came into play, so we got new scanning electron microscopes. Images looked a bit different, so we had to add them as well to our data set. And we also added images from other base materials of semiconductor wafers. So now we have around 50 classes in the data set, and we are down to an accuracy of around 85%. But the bigger the data set, the more complex it gets. And now we're trying to squeeze out the last few percent with these model-centric approaches. And then we're good to use it in the production.
So lastly, we have the deployment phase where the model gets deployed into the system. Since we have a 24/7 production, we would also need a 24/7 support on the model. This also includes a model monitoring, which can then, for example, look like this, where you have at the top the total amount of images classified by the model, then also a distribution for each wafer size and fabrication site, and on the bottom you have the average amount of time that it takes the model to classify the images. Challenges that we face in this stage are, for example, the deployment stability. We could have a decrease in the stability due to an increase or decrease of the production volume. Also, if we have an increase in the engineering data, the user acceptance is also a key aspect that we need to consider in order to make sure to include the users already at an early stage and show them how the model helps to make their lives easier as well. The model performance might also drop or vary over the time due to new inspection tools, new technologies, and therefore also new defect classes and types that need to be included into the model, and therefore the model update needs to be performed. For the model monitoring itself, we can have failure at various stages. Therefore, we need to break it down. So the first stage that needs to be checked would be the interface between the production and the model itself. Next would be the model. Here, a basic check is done on the prediction score of the model in order to find new defects already at an early stage, or see if we have defect classes which are quite similar and therefore get a mix of the classes then. Next would be the user interface or the inclusion of the user itself. So the model already does the main task of classifying the images, but nevertheless we need to make sure that the model works properly, so every nth lot would then also need to classify it manually, and we need to make a one-to-one comparison. Since we also want to check a long-term trend, we would then need to make a tableau graph where we can correlate the images per class as well as the prediction scores per class and find deviations more easily.
So, and now, after this super cool presentation, I can imagine that you would also like to work with such real-world data, and the good news is you all can, because we have published one subset of one of our data set, which we refer to as the Corinna data set. And how do we do this? Is we basically just download real production data from the history, and then what we have to do is we have to label them. And this image labeling is done at Infineon or in our groups with Label Studio. So this is a very cool tool for labeling. And we have defined there are 6 different defect classes and labeled all the images. And then we have uploaded it on Zenodo, so you can access the data set via this provided link here. And as you can, okay, now I'm somewhere on the link. And as you can see, this is really a real-world data set. It is highly imbalanced. And yeah, I encourage all of you just use it and work with our data set. And to wrap up the presentation, I would like to once more highlight that a huge team is required to bring projects like this to life in the production. And our team consists of experts from different fields, such as domain experts, data scientists, and ML engineers. Yeah, and yeah, a short side note, so please do not try to spot us among those adorable profile pictures. We've used ChatGPT to create them. Actually, my son over there, Elias, helped us, so he prepared the visuals for this presentation. Yeah, and yeah, last but not least, let's thank the big image classification team we are working in, because without their efforts, we couldn't be here today and present you this cool stuff. So thanks for your attention, and we are open to questions.
Thanks a lot for your interesting talk. Maybe there are some questions in, yeah, already here, Eva? Okay, you're next.
Thank you for the presentation. So I saw like you use the image NATE for the model, why not the other models? Like there are so many other transfer learning model which is better than this. So is there any particular reason to use this, or you have tried everyone and then like?
Yeah, we have done experiments with different architectures and different pre-trained models, and what we observe is actually whatever kind of model, even if we take the AlexNet, it works on our data set. So it's not, so they're all pretty good. And back then, when we started this project, just this efficient net were very, popular. So we still stick to them, although currently we are also training newer models. But what we see, they all kind of work. And for the last few percentage, we are now working especially on this hyperparameter tuning and just training different networks again and checking them.
Also, like, sorry.
Would you suggest a special model to try out on our data set?
Hello. Okay. So, I mean, there are like a VZ, this, and also I was curious about like why you are not using GNN graphical neural network for the image classification?
Graphical neural networks. Honestly, let's have a discussion afterwards. Huh? Thank you.
Yeah.
Thank you. If I think over there was another question.
Hi, thank you. One question, I think, to Isabella. You mentioned that this is for all wafer sizes. Is that correct, that in production it's 150, 200, 300?
It's working for various wafer sizes.
Okay.
So the typical ones that are currently used in the semiconductor industry.
And can you give us a flavor of the challenges which are maybe you find in 300 millimeter that you don't find in 150, 200?
Well, actually, for silicon, for the standard, it doesn't really matter if we have 6-inch, 8-inch, 12-inch. It's more interesting when you compare it to silicon carbide or gallium nitride, because there you find completely different defect types compared to silicon.
Thank you very much. Cheers.
Okay, maybe an online question? No, nothing? Ah, here is one more.
So thank you very much for this really amazing presentation, and also congratulations to your slides. So they're really great. My question is, what I saw about the application, it is more focused on production. Did you also think about the impact of defects on the chip structures and therefore provide some feedback on design rules already? So we know semiconductor manufacturing is very, very clean, but you never can avoid defects. So also to make or to support a more resilient design?
This is already done. So we are already thinking about with the manual classification, but of course we will consider it how to improve this with our automated defect classification.
Okay, one last question over here, and then I think we go on to the next talk.
Hi, thank you so much for the presentation. Just asking just out of curiosity, you as experts, you were mentioning that you're using two approaches, like model-centric approach and data-centric approach. I would like to ask, like, to what extent you're using these kind of approaches, like which one is more used in your field? And what are the advantages and disadvantages?
Yeah, I mean, we always start
with
the data-centric approach, because if you train a model on, low-quality data, you get a low-quality model. And what we observe in the real world is that you kind of gather a bunch of data, and you're pretty confident this represents the production, right? You train a model, and then you apply it on a new production period, and you realize, oh God, we forgot those technologies. They were just not produced back then, or products and stuff like that. So we always have to add new data. And also we have lots of classes where we have limited amount of samples, and we're always trying to fill them up. But those are just really rare defects, and so it just takes a long time to get enough samples in these classes as well. So we focus for a long time, we focus on these data-centric approach until we say, okay, now we are fine with this model check. We train a model, we apply it on new production data, and then we see, yeah, we get the same accuracy as on our evaluation data set, and then we are fine, we have reached this stage now, and now we're applying this hyperparameter tuning and training again different networks. And we also did this at the very beginning on the first version of the data set, just to figure out, is EfficientNet the best one, or should we go for another architecture like that? Yeah.
Okay, so I think we close this up here. The two of you will be at the lunchtime, I think, also in the study area. So feel free to get in touch with both and ask them lots of questions. Thanks a lot.
Thank you.